You know that HCP stands for hexagonal close packing and CCP for cubic close packing arrangement of particles. Now let us study hexagonal close packing. In this arrangement, the spheres are closely packed in successive layers in the AB type of arrangement, as shown here. Each unit cell has 17 spheres with radius r and edge length of unit cell 2r. Among these, 12 spheres are at the corners of 2 hexagons, 2 spheres at the center of the 2 faces, above and below, and the remaining 3 in the middle of the unit cell as shown here. You can calculate how many atoms or spheres each HCP unit cell contributes. Each sphere at the corner of a unit cell is shared by 6 surrounding unit cells. So, the contribution of the corner atoms to a unit cell is 12 into 1 by 6, which is equal to 2. The contribution of the atoms at the 2 face centers is equal to 2 into 1 by 2, which is equal to 1. On the other hand, the contribution of the atoms inside the HCP unit cell is 3 into 1, which is equal to 3. So, the total contribution is 2 plus 1 plus 3, which is equal to 6. Note that the formula to calculate the volume of an HCP unit cell is base area into height. The base area of a hexagon is equal to 6 multiplied by root 3 upon 4 multiplied by 2r whole square. The height of a unit cell is equal to 4r multiplied by root 2 upon 3. So, the total volume of an HCP unit cell can be taken as 24 multiplied by root 2 multiplied by r cube. Let us now see the formula for packing fraction. It is the ratio of the volume occupied by spheres per unit cell to the volume of the unit cell. The volume of spheres in this unit cell is given by V sphere is equal to 6 multiplied by 4 upon 3 multiplied by pi multiplied by r cube, which is equal to 8 pi r cube. Substituting the volume terms in the packing fraction term and simplifying, the resultant value is 0.74, which is equal to 74%. Therefore, the packing efficiency in HCP arrangement is equal to 74%. Let's study cubic close packing now. Let the edge length of a unit cell be A is equal to 2r. And the radius of each sphere be r. In this arrangement, each unit cell has 8 spheres at the 8 corners and 6 spheres at the 6 face centers. So, the contribution of the corner atoms to a unit cell is given by 8 into 1 upon 8, which is equal to 1. The contribution of the face center atoms is given by 6 into half, which is equal to 3. So, the total contribution is 1 plus 3 is equal to 4. Let spheres A, B, and C lying on the unit cell form a right triangle, as shown here. Then, applying Pythagoras theorem, we get AC square is equal to AB square plus BC square. Therefore, AC square is equal to A square plus A square, which is equal to 2A square. Hence, AC is equal to root 2A. However, face diagonal AC in terms of edge length is AC is equal to 4R. Therefore, equating the two expressions for AC, we get 4R is equal to root 2A. Hence, R is equal to root 2 upon 4 multiplied by A as given here. Packing efficiency is the ratio of the volume occupied by the spheres per unit cell to the volume of a unit cell. The volume occupied by 4 spheres is given by 4 multiplied by 4 upon 3 multiplied by pi multiplied by R cube. This expression in terms of edge length A is 4 multiplied by 4 upon 3 multiplied by pi multiplied by root 2A upon 4 whole cube. Hence, the packing efficiency in CCP arrangement is 0.7406, which is equal to 74.06%. You know that BCC stands for Body-Centered Cubic Arrangement of Particles. Let's now study body-centered cubic arrangement. In this arrangement, the particles are present at the corners and the body center lattice points. Each unit cell has 9 spheres with radius r. The edge length of a unit cell is A is equal to 2r. Among these, 8 spheres are present at the corners and 1 sphere at the body center of the unit cell, as shown here. You can calculate how many atoms or spheres each BCC unit cell contributes. Each sphere at the corner of a unit cell is shared by 8 surrounding unit cells. So the contribution of the corner atoms to a unit cell is 8 into 1 by 8, which is equal to 1. The contribution of the atom at the body center is equal to 1 into 1, which is equal to 1. So the total contribution of the atoms per unit cell is 1 plus 1, which is equal to 2. Consider points A, B and C on the unit cell which form a right-angled triangle. Therefore, on applying Pythagoras theorem, we can say AC square is equal to AB square plus BC square. Substituting the values, we get AC square is equal to A square plus A square, which is equal to 2A square. On the other hand, points A, C and D lying on the unit cell form a right-angled triangle. Applying Pythagoras theorem to these points, AD square is equal to AC square plus CD square. Hence, AD square is equal to 2A square plus A square, which is equal to 3A square. Therefore, AD is equal to root 3 into A. The body diagonal of a unit cell is AD is equal to 4R. Hence, equating the two expressions for AD, we can say that 4R is equal to root 3 into A. Hence, R becomes equal to root 3 upon 4 into A. Let us now see the formula for packing efficiency. It is the ratio of the volume occupied by spheres per unit cell to the volume of the unit cell. So, the volume of 2 spheres per unit cell is given by 2 into 4 upon 3 into pi into root 3 upon 4 into A whole cube. the volume of a unit cell is given by A cube. On substituting these expressions in the formula for packing efficiency and simplifying, we get 0.6805 or 68.05%. Therefore, the packing efficiency in a BCC arrangement is equal to 68.05%. Now let us study the simple cubic lattice arrangement. In this arrangement, the particles are present only at the corner lattice points of a unit cell. Each unit cell has 8 spheres with radius r. The edge length of a unit cell is A is equal to 2r. All these 8 spheres are present at the corners of a unit cell, as shown here. You can calculate how many atoms or spheres each simple cubic unit cell contributes. Each sphere at the corner of a unit cell is shared by 8 surrounding unit cells. So the contribution of the corner atoms to a unit cell is 8 into 1 by 8, which is equal to 1. This is the total contribution of the atoms to the unit cell. The volume of a sphere contributing to a unit cell is 4 upon 3 into pi into A upon 2 whole cube, while the volume of a unit cell is A cube. On substituting these expressions in the formula for packing efficiency and simplifying, we get 0.524 or 52.4%. Therefore, the packing efficiency in simple cubic arrangement is equal to 52.4%.